Hello everyone, this is Dr. Sami from the Biostatistics Learning Group. And we'll start from the book Pagano, Biostatistics, Fundamentals of Biostatistics, and it's a great book.
Biology.
Alrighty, so in chapter 2, they examine the descriptive techniques. Chapter 3, um, it's the numeric summary measures. Uh, Chapter 3 investigates descriptive statistics or techniques that help us to answer. Uh, and then Chapter 4, measurements that assume only two values. Then Chapter 5 introduces the life table, one of the most important techniques available for study in health sciences. Life tables are used by public health professionals to characterize the well-being of the population, and by insurance companies to predict how long a particular individual will live. So in this chapter, the study of the mortality begun in chapter 4, extended to incorporate the actual time to death for each individual. This is what they call the survival analysis. And then chapter 6 uh, applied to provide a means of quantifying uncertainty. Chapter 7, probability distributions. Chapter 8, sample mean or average. Repeated samples are drawn from the population. Confidence intervals and hypothesis testing are in chapter 9 and 10. Chapter 11, comparison of two means of two population means. Chapter 12, 13, continues development of hypothesis testing concept. And chapter 14, 15, and 16 develops inferential methods that can be applied to enumerated data or counts. Chapter 17 is which two factors are related to known as correlation analysis. So correlation. If you wish to predict the outcome of one factor based on the value of another, regression is the appropriate technique, where it's introduced in chapters 18, simple linear regression. In chapter 19, they have multiple regression setting. And then chapter 20, the outcome of interest can take on two possible values, such as alive or dead, or alternative technique must be applied. Logistic regression is explored in chapter 20. And then 21, inferential methods appropriate for live table are introduced. 22, fundamentals in inference, the concept of representative OS sample. So we have data presentation, table 2.1, table 2.2, or yeah. So types of numerical data, you have nominal data. So table 2.1, it's outcome indicating whether an individual had Kaposi sarcoma for the first uh, 2,568 patients were to the Center of Disease Control and Prevention in Atlanta, Georgia. Although these attributes are labeled with numbers rather than words, both the order and magnitude of these numbers are unimportant. We could just easily let one represent females and zero designates males. Numbers are used mainly for the sake of convenience. Numerical values allow us to use computers to perform complex analyses of the data. Nominal data can take on one of the distinct values, such as male and female, are said to be dichotomous or binary, male and female, depending on whether the Greek or Latin root for two is preferred. However, not all nominal data need to be dichotomous. Often there are three or more possible categories in which the observation can fall. So ordinal data, that has an order to it. So when the order among categories become important, the observation will refer to ordinal data. So you've got table 2.2 that provide a second example of ordinal data. The scale displayed is used by oncologists to classify the performance status of patients enrolled in clinical trials. Clinical trials is an experimental study involving a human subject. Its purpose is usually to facilitate the comparison of alternative treatments for some disease, such as cancer. So Eastern Cooperative Oncology Group classification of patient performance status. 0 is patient is fully active, 4 patient completely disabled. So here is a ranking to it. So it's a ranking and order to it. So it's an ordinal data. So rank data, this type of data is known as rank data, where you have observation that refers range from highest to lowest according to magnitude, and then assigned to numbers that correspond to each observation place in the sequence. And then you got discrete data. Both ordering magnitudes are important. In this case, the numbers represent actual measurable quantities rather than mere labels. So in addition, discrete data are restricted to take on only specific values, often integers or counts, that differ by fixed amount. No intermediate values are possible. Examples of discrete data include the number of motor vehicle accidents in Massachusetts in a specified month, the number of the times a woman has given birth, the number of new cases of TB reported in the US during a 1 year period, a number of beds available in a particular hospital. Note that the discrete data natural order exists among the possible values. If we are interested in the number of times a woman had given a birth, for instance, a larger number indicate the woman has more children. Furthermore, the difference between 1 or 2 births is the same as the difference between 4 and 5 births. Finally, the number of births is restricted to the non-negative integers. A woman cannot give 3.4 times. So if it's 3.4 times, then it's continuous, not discrete. So that's what's the difference between discrete and continuous, because it's meaningful to measure the distance between possible data. So you have here table 2.3. This is the 10 leading causes of death in the United States. And here, this is our discrete data. So one is disease of the heart, 2 is malignant neoplasms, C or 3 is cerebrovascular diseases, and 4 chronic obstructive pulmonary diseases, 5 accidents and adverse effects, so on and so forth. So continuous data, that what has this continuum, which we mentioned, it has integers to it. For example, 3.5, 3.6. So continuous data represent measurable quantities, but are not restricted on taking a specified values such as integers or non-continuous data. And this, the difference between any possible data can be arbitrarily small. Examples of continuous data include time. The serum cholesterol of a patient is the concentration of a pollutant, the temperature. In all instances, functional values are possible, fractional values are possible, since we're able to measure the distance between two observations in a meaningful way, arithmetic operation can be applied. So the only limiting factor for continuous observation is the degree of accuracy, which is measured. Consequently, we often see time rounded off to the nearest second away to the nearest pound of ground. So in section 2.1 describes the gradation of numerical data that ranges from nominal to continuous. As we progress, the nature of the relationship between possible data values become increasingly complex. Distinction must be made among the various types of data because of different techniques are used to analyze them. Thank you so much. By this, we conclude our session, and then we'll continue to the next session. Please follow us on Twitter on this account. And thanking you so much for your time.